Hello, this is the workshop 3, my presentation on the simplex algorithm and how you can use it to solve linear programs to find a maximized value. So a linear program is a mathematical model that we can use to optimize different problems. And the way we do that is by defining the problem through linear equations and equalities or inequalities. And for many problems, you might have limited resources such as time and money, and you want to allocate those resources as efficiently as possible to provide the most value back. So one way we can represent this is the function of v equals 5 times v1 plus 3 times v2 plus v3. And v is a set of variables, v1 through v3. And we can use linear problems to solve something like this. For example, a farmer at the farmer's market has a limited amount of space that they can sell their harvested fruit and vegetables. And we assume that everything is sold by the end of the day. We know the prices for each specific fruit or vegetable as well as their size, but we would like to figure out how to make the most profit. So we could create a set P for the produce, and I named the variables such that we could understand that one is tomato, one is watermelon, and the others are carrots, just so it's easier to differentiate. And we then have an equation for the total price we would get back based on how much we sell. So let's say $2 for tomatoes, $3 per watermelon, and $1 per carrot. And then we would have a linear equality where you can only fit so much of your produce in the space you have. And I just decided that we would go with 50 cubic meters. So a tomato takes up 1 cubic meter, a watermelon takes up 5, and the carrots take up 2. So the goal is to sell the most and make the most profit, but we cannot go over the constraint of space. And this is very similar to the knapsack problem that we covered before. And with what we learned there, the best choice for this case would be to sell tomatoes, as they have the greatest ratio of price to space it fills up. In modern applications, there are many more constraints that we have to consider though. Maybe the farmer has a limited amount of each produce, so instead of selling 50 tomatoes, the max they could sell is 30. And maybe the farmer's market enforces them to have an even spread of fruits and vegetables. So they have to include an equal amount of carrots or tomatoes to the amount of watermelon they sell. Linear problems can end up having even more variables as well as more than one constraint. And then there's a bit more I'd like to cover before we look at the simplex algorithm. The forms of a linear program, we have the standard form, and we create a vector of size n called C, and it's just real numbers that will act as the coefficient to our variables in the objective function, which is what we try to maximize the problem to. And we will also have an m vector b, which is of size m of real numbers, which serves as the constraints. And we will also have an m times n matrix denoted as I of j, where I is from range 1 to m and j is from 1 to n. And we can convert the standard form into a slack form where we want only non-negativity inequality constraints. And for every other constraint, we want to make it an equality instead. And to do this, we end up creating a slack variable which holds the difference between both sides. And we can put the constraining value on the same side as the objective function. So now we have a summation where the objective function is z equals v plus the summation of the variables and their coefficients. And for the constraints, we have x of I equals to b of I, which is going to be the slack, minus the summation of variables with their coefficient for anything contained in set B. And we let z be the objective function to make things simpler for ourselves. And x is another vector of length I to hold all the constraints. So we can have only one objective function, but we can have multiple constraints. And that's why we end up having a matrix down here rather than a single length, like a single dimension matrix. So this ends up covering all possible constraints where the I moves through the rows and the j is the column. So now that we did that, I'll show you what the pseudocode for the simplex algorithm is from our textbook. And with a linear program translated into a Slack form, the simplex algorithm will perform successive pivots to maximize the variable in the linear function and return the most optimal solution. And for the input, it can just take a standard form because at the first line, we will generate a Slack form for it. And if it doesn't find an optimal solution, it can end up returning the statement unbounded or infeasible as well. We will cover that in some other issues as we go. So for the code, we denote a Slack form as a tuple with the values n, b, a, lowercase b, c, and v. And we have it such that n is the set of non-basic variables, which is the variables we have on the right-hand side. B is the set of basic variables, which is on the left-hand side. And the non-basic variables are like new variables that we introduce when we convert from standard to Slack. The basic variables are the original variables we had in the solution for the, or not the solution, for the standard form. And then A is the set of values of lowercase a of ij. Something important to note is that the values are negated. So what you would see in Slack form, it is stored as a negative value in this set. And then B and C holds the coefficients the same way as they did before. And V is the optional constant value, which is in the objective function. We don't really need to worry about that in this case. And I first wanted to point out the auxiliary methods, which are other functions that are called in this algorithm. The first one I'll cover is pivot, and this is the core for the main simplex algorithm. It does, it follows what is called the pivot rule, which makes up how the simplex algorithm works. And what you do is you pick a variable that will enter and a variable that will leave. The leaving variable will be going from the left-hand side to the right-hand side, and vice versa for the entering variable. And what it does is they swap places, and that's why they called it pivot. It ends up pivoting around a variable and replacing it. And what we end up doing is creating an equivalent algebra expression by swapping a basic variable with a non-basic variable. And everything on the left-hand side is basic when it comes to the variables, and non-basic if it's on the right-hand side. So looking at the pivot method, if we were to write out the equalities, you could see it as an algebraic expression where you have to balance the sides if you want to move a variable over. And for lines 1 through 6, we update and we generate new coefficients of the equation for the new basic variable x, or the entering variable. So now that that variable is basic, we end up updating the slack variable, and then we iterate through the non-basic variables excluding um, the entering variable, and we adjust the coefficients as well. So for the slack variable, we have to divide the old slack variable at the index L by the coefficient found at index L and E. And then we iterate through every j contained in set n, which would be um, every variable in that row, I believe. And then we update the coefficients such that the coefficient at, we get the new coefficient at E of j by dividing the coefficient from spot L and J divided by spot L and E for coefficients. And then once we go through everything but the entering variable, we can adjust the coefficients separately, and it's just 1 divided by the coefficient at index L and E. And then when we go through lines 7 through 12, we compute the new coefficients for the rest of the constraints. So we have to iterate through each basic variable excluding the leaving one. So this one ends up being a nested loop instead. And then the slack variables for each I is computed to be itself minus the coefficient at spot IE times by the new slack variable at index E that we found on line 3. And that was for line 9. It then iterates through every non-basic variable excluding the entering one. And we update the coefficients by taking the old one and subtracting it by the coefficient at index IE again, but this time timesing it by the coefficient A at spot E of j, which was calculated in line 4 in that loop. And then once we do that, we return to the index of the entering variable, and we set up the coefficient at spot I of L, I and L, equal to the negative coefficient at I of E again. And then we times it by the new coefficient at spot E of L. And then for lines 13 through 12, we will go through and generate the new objective function. And we have to increase the optional constant by the coefficient at index E times by the new slack variable at index B. And then for the rest, we just update the non-basic variables on the right-hand side by taking the coefficient and subtracting the coefficient at index E times the coefficient at E of j in set A instead. And then once we do that, we return to the spot exclusively where the entering variable is. And we do the same thing, except it's just equal the coefficient at index E negated, and then times by the new coefficient at index E of L in set A. And then once we get through that, all we have left to do is to generate the new sets. And to do so, we take the old one, we remove the entering variable from the set N, and then union it to add the leaving variable. And then for set B, we do the same thing, but vice versa. We take out the leaving variable and union the entering one in. And at this point, we will have swapped the two variables, and the new Slack form will be equivalent. And the objective value, when calculated, will either be the same as it was before or higher. And that's the trick for that. We will perform successive pivot calls in the main algorithm until we reach the maximized solution. But first, I'd like to also cover the initialized simplex. This one is covered much later in the textbook, but I wanted to get it over with now. This method is used just to create a Slack form for the standard input. But what it will also do is determine if it has a feasible basic solution. And it's possible for the standard form to not have that at first. And if that's the case, this function will attempt to look for it by pivoting with a new rule. And if it fails to do so, it will just return the statement infeasible, and the main algorithm will end as well. So this one takes a standard form input, and it will attempt to find the basic solution. So it'll just grab the smallest Slack variable. And if it's positive, then we know that there are no negative Slack variables, and the basic solution will be feasible. And this follows a rule where we know that at the basic solution, we would set the solution equal to the Slack variables, and everything else gets zeroed out. So if we find that the Slack variables are positive, then we will have positive solutions as well. But if we can't find a feasible solution right away, we will create an extra non-basic variable denoted x sub o, and we will use that as the entering variable for a pivot. And then for the leaving variable, we will decide it to be at spot k, or the minimum Slack value added by n. And we can assume that there are a total of n plus m indices for x that we could choose from. So k must be less than or equal to m. So we can't go out of scope with that. After we pivot, we end up with a new Slack form that can have an objective value of 0, which we use to prove that the original linear program does in fact have a feasible solution. And then we will keep iterating the same way we do in the main algorithm until it can set x sub 0 to 0 while it is basic. And afterwards, it'll perform what's called a degenerative pivot, which will make it non-basic. And since it's equal to 0, we can just remove it from the equation, and everything will still be equivalent afterwards. If we end up with a negative optimal objective value instead, it will get through the while loop and reach the end line and return infeasible instead. So to summarize, the pivot will take negative Slack values and make them positive, and it will do so until it can find x not being equal to 0, and then it will remove it from the equation. And despite performing successive pivots, the goal for this is to get the most optimal feasible basic solution, not whether or not it's maximized. That's what the main algorithm will handle from there. So now that we know how the auxiliary methods work, we can examine the rest of the algorithm. So we create a new vector delta to hold our values, and we iterate through another while loop from line 3 to 12. And we will go until we have no more positive non-basic variable coefficients. And within the loop, it'll choose an entering variable and cross-check that index with E with all the basic variables to check for any negative values. And if it does find a negative value for that variable, it will mark the value in the new vector delta as infinity. And what this does is it accounts for the possibility that the linear program is unbounded. And that happens when you have a variable that can increase to infinity without ever violating any constraints. And if we have this happen, we will return unbounded. Otherwise, we will begin to pivot, and the leaving variable can be freely chosen as whatever basic variable minimizes the value the most, whichever constraint is the tightest. And then that will be how we decide to pivot. But with this pseudocode, there's no deterministic rule for choosing the entering variable, besides the goal of picking a good leaving variable. What this code assumes is that it's already specified beforehand. And then when we reach the end of the while loop, it will return a new slack form, which is a final iteration that's still equivalent. And it'll develop the solution set from that, denoted as x naught, from range I to n, I equals 1 to n. And the solution is found by setting the solution values equal to the slack values for every constraint, with the non-basic variables being set to 0. And then if you were to go back, you could take these values and plug it back into a linear program, and you would see that it provides the highest objective value. So the goal is to maximize it, we increase the objective value as much as we can without violating any constraints or reaching an error. So I'll cover the time complexity analysis now, and it's a bit weird. The first thing I can do is show the time complexity for the pivot method. And I said let x equal the number of items in set n minus 1, which would account for the entering variable leaving it. And we do the same with y equal the number of items in set b minus 1, because we have 3 loops. We have 2 loops that'll iterate through the set of n, and then we have 1 loop with a nested inner loop that'll iterate through both sets. So loop 1 is calculated to take big O of x. Loop 2 is big O of x times y. Sorry about that, there's a typo there. And then loop 3 will be lines, will be notation big O of x. So it's linear up until the middle loop where we get a running time of O of x times y. And that's what it simplifies to. And since we have equal vector sizes that hold the same values as what we find in the set M of n, we can also just use M and n as the variable, so it's bound by what we see in the new matrix, for example. And then I also wanted to make sure that if you were to develop code to remove something from a set and union it, that might have a big impact on the time complexity. But that can also be managed in linear time, so we don't have to worry about that. And then for both the initialized simplex and the simplex, it's much harder to analyze this. The reason I include them both is because they both have a somewhat similar while loop situation. And what they have found in research is that some problems can cause it to run indefinitely. So you could include an additional check where if it iterates through n plus m, choose m, combination of iterations, then it will cycle at that point. So they've determined an upper limit of how many iterations you can go through before we reach the point of degenerate pivots where um, we can end up going back and forth and swapping the same two variables, or creating a loop where we swap two variables back and forth and then go through a pattern. And the pseudocode we get in the textbook isn't the most directly applicable version of the simplex algorithm. From what I looked into it, this seems to be more theoretical and more of a method. And there are several other versions of it that might get covered by other students. So I didn't want to touch on it too much. But you could see here, we also have the network simplex algorithm, which is one of the closer. Like this one is very similar to just the simplex algorithm as it stands. They can end up using the same pivot. But the algorithm runs faster than expected in many situations. And there's been lots of research into why that's the case. So it has been found that the expected case could run in polynomial time. And this was done through the works of Daniel Spielman and Xinghua Teng. Pardon me if I didn't pronounce the name right. And it is possible to randomize choices with what they found and redefine the pivot rule. They call it the shadow pivot. And what it does is increase the chances that you'll end up with a linear program that can be solved better than the worst case. And then there was another thing figured out in which they could determine the worst case for the simplex algorithm. And this was done by Victor Klee and George J. Minty. They developed a specific set of problems which can be called the Klee-Minty queue. And the textbook specifies that with their example, it would require 2 to the power of n minus 1 iterations. In other words, the worst case time would be exponential time. And now we'll cover the proof of correctness. So we'll make some assumptions based on the auxiliary methods first. So long as we don't have a value of coefficient at the spot L and E equal to 0, we can run the pivot function without any issue. But we have to keep watch on that because that is used to divide by, and we cannot divide by 0. So the pivot function, while it works, will return a basic solution with these characteristics. All of the non-basic variables can be equal to 0 in the solution. And then the solution of the entering variable will be equal to the original slack value at index L divided by that coefficient we talked about earlier. And the solution for the leaving variable will be equal to the old slack at index I minus the coefficient at I of E instead, times what they denoted as B at index E hat, which is the new slack variable at index E, for every basic variable except the old entering variable. And when it comes to the invariant loop proof, the pivot maintains a basic solution, which can also be used to find feasibility, and it'll also generate equivalent slack forms that remain feasible. So we've already seen that the time complexity is pretty spotty, and the algorithm seems more theoretical than fully understood. One example of a more concrete version would be the shortest path algorithm. But what the textbook we have for our class does provide is that it'll prove that it terminates and that it will reach a global optimal value with the concept of duality. So for our loop invariant, this is based on the while loop from lines 3 to 12. At each iteration, we will have a slack form that is still equivalent to the previous one, or equivalent to the initialized one provided by the initialize auxiliary method. 2, we will have every basic variable in set B be non-negative, which is just greater than or equal to 0 in this case. And 3, the basic solution for the slack form is feasible. When we first call the initialize simplex method, it is possible for the slack form to not be feasible. So in the initialization step, we have to try to search for that. Otherwise, we end here. And thanks to how it works, we can complete the first iteration and neglect that the feasibility of the initial input isn't there yet, because when we go through, if we can find a basic solution that's feasible and we can prove that it's equivalent, then that means there is a feasible solution from the initial input. We just have to look for it. And then at line 1, we determine whether or not that is the case. And if we do not find a feasible basic solution, we will terminate the algorithm with the message unfeasible. Otherwise, if it does return 1, we can confirm that all the basic variables are non-negative. When we have a basic solution, we set all the non-basic variables to 0, and then the basic variables will be set equal to the slack variables. And because the slack form enforces non-negativity for the slack variables, they will be positive, and we can guarantee that the solution will be positive too. And that's how we prove that all 3 parts of our invariant loop hold true at initialization. And then for maintenance, at each iteration of the loop, we perform a pivot call and generate a new slack form. The pivot call will guarantee that the new slack form is equivalent to the prior, as we've seen before. And the basic variables will be positive. And this will hold true because the updated slack variables are not formed with negative values. And the way they prove it is we look back at the way we generate the new values. When you divide by the coefficient at the spot L of E, it'll be a positive number. But in the statement where we subtract it, at spot I of E, it's possible for it to be positive or negative. If it's positive, then it'll cancel out with the new slack variable at index E. And it'll be equal to 0. It'll get zeroed out. But if it's negative, then it'll be a minus, which will make it positive instead. And the new set of solutions generated are made equal to B at index I as well. And since that is non-negative, we assure that the solutions are as well. And the basic solution is feasible. For the termination, it'll terminate the while loop with 2 different paths to circumstances. The first one is we have no more non-basic variables with a coefficient greater than 0. And the other option is that the problem is unbounded. If we reach the first situation, we will terminate the while loop to prevent errors during the pivot method call. Since we have to perform a division with that 1 coefficient, we stop before we terminate the loop when we find that there are values that are close to that. But we will end up finding a slack form at that point that is still equivalent and has the highest objective value that we found yet. And if the problem is unbounded instead, we would still have an optimal solution. The issue with that, though, is the maximized optimal solution. would have to be found at the end of infinity. So the way they denote it is that the the most optimal solution is a finite one. And if we return unbounded, then we found that it isn't a finite one. And then we can also prove that the final slack form after the loop terminates is optimal with the concept of duality. And this is something we can apply to any linear problem. If you take a linear program, you can build a dual linear program off of it, which is we create an extra linear program that is minimization rather than maximization. And to do this, we take the original one, we swap the roles of the coefficients on the right-hand side and the objective function, and then we will swap all of the less than or equal to equalities to greater than or equal to. And then we'll start to use the variable y of I as an m vector of size I, and x sub j for the n vector of size j. And then when we do that, that one would be called the dual program, and the original one is called the primal program. And if we can generate this and compare it, we can prove a few useful things, such as if the objective value from both of them is equal, then that is the global optimum. Otherwise, we can at least show that since one is greater than the other, we have an optimal solution at least. And then for this, I talked about it just before, but for hopefully a better understanding, the reason that you reach a global optimum in that case would be because we can't have the feasible solutions for both problems overlap. So the duality of it is that the max for the primal is the minimum for the dual, and if you were to increase the maximum, you would have to decrease the minimum. And then because we terminated the loop with a situation where we do not have any positive coefficients for each j in sets n and b, what we end up doing is satisfying the constraints for a dual program where all of the y at index I naught will be non-negative. We can likewise build a feasible dual program out of the feasible primal program we created. And because we have feasibility on both sides, we are guaranteed to terminate with an optimal solution on this path. And then I wanted to talk a bit more about if it's a global optimum or not. The textbook goes in a bit more detail about why the simplex algorithm reaches the global optimum. And if you were to look at the simplex algorithm in other terms, a linear program generates a feasible region which you can graph, and it ends up being a shape that is also convex. And because the objective function is a linear, we can use those two facts to prove that the optimal value we find ends up being the global optimum. Because the way they described the simplex algorithm early on is that it travels along the edges and vertices of a simplex, which is the representation of a feasible region in the graph. It's like a polygon or a shape. And unlike some of the other potential solutions and algorithms they came up with, this one will stay on the exterior of the simplex, and it can always reach the global optimum because it is convex, unless it ends up with an endless cycle case. And the nature of it being convex is sort of like it being rounded. So there's not an extreme edge on the shape that it can get stuck on when chasing down an objective value. But they did in fact find a feasible region in the shape of the Klee-Minty cube that would always cause worst case problems. And what that ends up doing is it forces the simplex algorithm to travel to each vertex, which is there's 8 of, and then to make up for the lack of concrete time complexity in proof. I have some very recent studies on something called NP-MIghty. So there's a thing called the NP-MIghty algorithm, and this was based on the research of Jan Dezer and Martin Scudala. Pardon me again if I did not pronounce those names correct. And they said that an NP-MIghty algorithm is one that implicitly solves a particular NP hard decision problem and implicitly solves all problems in NP. So what this means is that an algorithm can solve NP hard problems during its runtime, not that it reaches the solution for the NP hard problem. You could imagine if you just took an algorithm while it was running, pause it at a specific time, see inside of it, and realize that it managed to solve an NP hard problem while it was working, and it won't announce it. So what their research was is trying to find a new way to look at an algorithm and try to figure out why it runs the way it does. And their goal was to prove that if it could solve an NP hard problem, just trying to solve the original problem it's working on, then that would explain why it might take so long with the worst case in this example. So what makes the simplex algorithm NP-MIghty? The paper finds the results that when using the network simplex algorithm, implying the original method as well, because they share the same pivot rule, they found that they can solve the partition problem implicitly. And then going a step further than that, they found that any NP problem can be solved implicitly within the simplex algorithm. And so here are my references. From the textbook, you can read about the simplex algorithm at chapter 29. Sections 1 to 2 provide context on how to set up the problem in standard and Slack forms. Section 2 also talks about the types of problems you could solve, so you could learn more about that. It begins to cover the algorithm from section 3 onwards. And then for the research article just mentioned, it is called The Simplex Algorithm is NP-MIghty, and it was released in 2019. And I have a link to the PDF here. And I know this one was a long one and it's very confusing because there's many variables to keep track of. So if you guys have any questions, please ask, and I'll do my best to go back and reiterate and make any corrections and otherwise try to help you understand. Thank you.